So the first thing I want to do, just to maybe wake us up a bit, is I put it in the Slack if you want. If not, I also put it on the Google Drive. I want to play a little game, a diffusion game with you. So we have a little app that I wrote a while ago that allows us to simulate a, where did I put it? Here we are. So if you go to the Slack channel, you'll find the link to this here. Let's reload it. If you don't have, if you're not on the Slack channel or you don't have it, there is R code underneath it. You need to copy everything from the folder on the Google Drive into the same directory of your own machine if you want to run it locally. So what this is the Shiny app, and it's a Shiny app that allows you to upload your own data and play with it. It also comes with a set of preloaded data, and I'm just going to walk through a little example to show you how this little toy works. So I have the Zachary Karate Club, for example, and I can load the network. And so here it is. And if you look at this network, you can get in there and you can move it around. And so it's using some of the Viz network tools that are nice for that. And what we're doing here, I typically do this because what we're going to watch is where the diffusion goes. So I like to unstack the nodes a little bit. You get a layout you like. You can save the layout just so it then doesn't move around. If you have ever played with Viz network before, it's zoomable. It has a series of highlights that go to it and things like this. So it's a pretty clever little set, and we'll talk about that a little bit more at lunch. But the way this game is set up is that your little community is going to get infected by a bug. And you need, as a good public health worker, to figure out who to vaccinate. And what vaccination strategy is going to give you the highest return. Now, you have a series of parameters that describe you the number, some numbers that are useful. So in this case, we have the likelihood that an infected person infects a susceptible person. So in this case, I say it's about 30%. We have the length of time people are infected on average. So it takes about 5 days for 90% of people who've been infected to recover in this particular example. I'm going to say that my vaccine is pretty effective. I'm going to say it's like 80% effective. That's not so bad. And that the probability of recovering from, of becoming severely ill, about 20% of my people are going to become severely ill. It's a small network, so 20 days should be enough to do this. And then what I can do is I can either, let me unset, let me clear my sets. Why is that still yellow? Reset selection. We might all be on it and slowing it down. That's funny. We might be breaking it. I'll just run mine local. That'll work. So I'm doing the same thing. I just ran mine local here because for some reason the web is going slow. Now what you can do is say, let's put this back to about 0.8. And if I have nobody vaccinated, which is sort of life in the wild, and I say just run 5 of these, what you'll see is it's going through and people get infected. They recover if they're gray with a circle around them. And otherwise, it keeps going. And at the bottom, you can see your diffusion curve. So this is a classic, sort of very simple point of contact simulation where each person who's infected has an opportunity every day to infect their neighbors. And if their neighbors get infected, they infect someone else. And this is kind of what you always see in a simulation like this, is that you have some level of growth, but there's also a high variance. So in about 2 of these cases, of the 5 cases I ran, nobody got sick because the initial person never ended up infecting someone the next time. There's only a 1 in 3 chance that we do, and they recovered before they were able to infect anybody else, and so the infection died out. On average, you get something that looks like this. Now if you were to go through again and say, let's take the exact same network, I'm going to reset my selections, and I'm going to infect Let's see, there's about 35 people in this network, I think, so I'm going to infect, or I'm going to take my 2 most central people and, I don't know, let's see, 3 people in the middle of these clusters. Now, the infection source is random, so I don't know where it's stopping, but my theory of the case is that bridges and centrality are where diffusion stops, and so I can go through, and then everything else is exactly the same. I will run a batch of those. Let's see how that works. And now we have a series of curves that are in the world where you have some vaccinated and we have some don't. We can look at the currently infected set versus the cumulatively infected, the number of severely ill. It doesn't look like I did a whole lot of good in this case, vaccinated versus not. So we find that the number of people who were currently affected at any given time was this essentially that disease curve lasted a lot longer. There were people. Well, let's do the cumulative first. It'll be easier to see. That's too bad. In this particular case, we ended up with more. Don't tell anyone. We ended up with more infection on average. These are different seeds that got started with, I think, if I remember correctly. We ended up with more infection with some vaccination than we did in the case it was not vaccinated because we didn't have as many people at 0. Right? So this is why you never run a simulation with an N of 5, if we're honest, right? So if I were to do this again, your results may vary, I would suspect. But this is a fun little game, and you can do it with any kind of set you want to do. Let's reset the selections. And the beauty of this, and one of the things that I like it for it, because it's fun to tell audiences with, is that it really takes a lot of work to stop a bug. Right, so even when I have an 80% effective routine in something like this, I'm going to clear my series so we can get a new set, run a batch again. Because this is never effective, you'll notice when it flashes it goes all over, that we end up with often a slow growth, but almost very, very rarely a complete stop. And so if I really wanted to kick this thing into gear, I would probably need to both make a much more effective vaccine and, more importantly, I would need to, it's a little boring to watch me click everybody's case here, but you need something much higher than that. Now, the key to this, and this is the reason I wanted you all to see how it looks and what it works like. Did it work? There we aren't quite as many. Even then, see, you get breakouts. Now we're not the percentage of total is smaller. We're at 70 now instead of 100, but it's still a lot of people are still getting sick. Now, what I hope for you to do, and this is why I love these kind of intuition tools, is that spend a little time, especially if this is the world you live in, playing with this kind of a thing. And you can do it on any kind of graph you want. When you upload your own data, it's just a two-column CSV of a sender and receiver, perhaps a weight if you want, and the likelihood of infection is proportional to the weight of the edge. So if you have a weighted graph, it respects that. It's interpreted as opportunities for contact per day, so that's the way the number is scaled under the hood for an edge weight. But you'll see that it's just real. The networks are tricky, right? You can slow these things down, but it's really hard to stop them. And you can find many different ways to do this, and it's a great way to build intuition. And so what I was hoping to do then, after sort of you playing with that, is to ask ourselves, slideshow, slide, is how do we build that intuition, right? So what is the thing we actually do when we think about a diffusion in a network? As a general case, network diffusion, when we say network diffusion in a social networks audience, it means 3, maybe 3.5 different things. There is what I just showed you, which is disease spread. But all of them have in common this notion that what we're talking about is how actors change states in a network, conditional on the states of their neighbors. That's what diffusion is. So every neighbor has a state. That state changes because of something my neighbors are doing. So all of these models have that underlying formalism, but there's a whole series of different models that are here. And so the classic one that we play with is disease spread. And so the idea that a susceptible person infects an infected is the likelihood that a susceptible changes their state from susceptible to infected because I bumped into somebody who's infected. The adoption of innovation is that I won't use R because it sucks, but I hang out with a lot of people who do, and before you know it, I'm using R. So that's an adoption set. It's exactly the same as a infection model, except the agency differs, like the reason why it happens. I don't say, it looks like having the flu would be a lot of fun. Let me go out and get it, right? So the agency differs, and there's this whole wonderful world of things called threshold models, that the amount of exposure and the diversity of exposure changes. And so there's a whole series of models that build into that, but you move from non-adopter status to adopter status, and there's various versions of that. And then finally, there's this blending model of state change, or continuous state change, which is essentially the logic under the hood of peer influence models. Is that you believe that turnips are delicious. I think turnips taste like dirt. We sort of hang out for enough time. You show me some good recipes, and I come to realize that once in a while I can eat turnips, right? And so we meet in the middle around these ideas. And so there's some range of beliefs, and we find some way of consensus to getting to them. And the field has generated a bunch of different tools for doing all this. And I'm not going to go through those tools today. We just don't have time. I thought I beat myself up earlier last week thinking if I was a better person, I would do that. But I think that I'm going to focus on the intuition instead. But if you're interested in disease, you should know about EpiModel. EpiModel is a great tool. Sam Jensen has demonstrated that tool in this workshop. It's recorded. It's on the website. You should find it. If you're interested in the adoption of innovations, you should know about Net Diffuser. This is Tom Valenti's software that lets you specify ex post from the history of adoption what people's thresholds are, whether they have a high threshold for adoption or a low threshold for adoption, and how that is affected by their neighbors around them. Similarly, for peer influence models, we're going to talk about a lot of those models the rest of the day as well. So we have, if you have a static network, we can fit these models pretty well. We're using variants of network autocorrelation models or spatial regression models, and the StatNet tools have a function called linear network autocorrelation model, LNAM. So that model is right there. If you have a stochastic model, you want to use a stochastic actor or a dynamic model. There's a stochastic actor-oriented model, which is, or otherwise sort of affectionately known as a Siena model. And these models allow you to have people state change and edge state change simultaneously. And so they work quite nicely. Many times, despite how brilliant a lot of these models are, we grow our own. And so I'm going to show you a lot of the models that we grow our own and why you might grow your own, because we want to answer a very specific question. And I think there are a lot of, it turns out that very few of these models by themselves can account for really complex social phenomena. So if you're dealing with something, for example, like a disease moving through a population and people reacting in real time to that disease flow, then you need a way for people to adjust their contacts, to change their ties around them. And so you'll have simultaneously a knowledge thing moving through the network and a disease moving through the network, and those feed back on each other in really interesting ways. And thus far, some of Siena models get close to that now, but thus far the models really aren't generated for doing that. So what do these models look like? Much like the ergom discussion I did a minute ago, we can think about the ways in which things move through the network as sort of a simple version and a complex version. And the complex version is really, in many ways, a very fine-grained simple model. So we take a simple model that we do on aggregate, and we break it up into lots and lots of little pieces, and we get a complex model. Now, how you break it up and the way you link those pieces is non-trivial, right? But the intuition is sort of built on that kind of idea. And because all of us went through the last 5 years, I think everyone in here is older than 5 years old, right? Yes, because that's true, we've also already seen this, right? So we know what this is. This is a compartmental disease model where people move from a set of 4 different compartments. And so you move from being susceptible to exposed to being infectious to being recovered. And with some probability, each of these Greek letters, you move from here to here. Your world in each state, the thing that you are here, is the same as everyone else. This model only knows this. It knows everything you see in this screen. And so everything in this model is homogeneous. It's a homogeneous mixing model. And it's a uniform action model that everyone here has an equal probability defined by this critter, which is down here, to move from changing the infection happens here, And so you can see what these equations do, right? It's a closed form set, and they're beautiful models, right? They're elegant models, but they're not particularly realistic, right? And the reason they're not realistic is because real networks look like this, and homogeneous networks look like this. So real networks have lots of these little clusters and different paths and so forth that make the assumptions built into this uniform set unrealistic. So we need something to account for that realism. And the best way to do it, that has been done a lot, is to say, let's just make a compartment for the green nodes, a compartment for the red nodes, a compartment for the purple nodes. And if I know how my network is clustered and that clustering is really high, those models work pretty well. They are non-trivial, particularly when the probability of infection between a particular infected person and their partner is high. If spread is likely, or it's, for example, because it's airborne and we're all in the same room together, right, these models work much better than if it requires intimate social contact. So if in order for you to get the bug from me, we have to be in a dark room with our clothes off, like that's an unlikely thing to happen rapidly. Right, so we need a way so those things move slowly. So PIJ, this infectivity parameter, I don't know why I call it that. I'm sure there's better, more standard nomenclature, but this is the probability that I infects J, and so you have some amount of time. This is the governing feature, right? So for disease spread, you cannot ignore the biology of the virulence of the bug. Biology of the virulence of the bug is primary. Given that, all of this other stuff can happen, right? So you're never going to win a drag race, like in my old Volkswagen Beetle. So it's like how fast your engine is. That's the infectivity of the bug. But once you have that, you can tune the tires and think about the track and things like this and how fast you go. So what are the tires and tracks? Like what are the things that govern the spread of disease or the spread of information or the likelihood of adopting across a network conditional on the graph structure? And I break it up in these two buckets. There's one bucket of things about the shape of the network, and there's another bucket of things about the timing of relationships on the network. And I'll talk a little bit about both of them as they go. So there are 5 basic features that govern the spread of something through a network. And so this is the reason I wanted to play with that little intuition game with the simulation is that when you want to pick the optimal place to put a vaccine, you're probably going to play with some of these features. So if we had more time, after this session, you should be able to do a better job of that game than you did before that session. But I'm going to give you the answer now so you can see where we're at. So there's some necessary features that have to do with probability and the fact that we change states conditional on our neighbor state, which is reachability and distance. You can't spread a bug through a network unless that network is connected. Like a room full of isolates are never going to get sick. And that's the great thing about going and living in the woods, right? You can live in the woods for a long time. You never see anyone. You have kids that go to school. New teachers, like the first 6 months of being a new teacher is the worst, like the disease world you'll ever go through because you've been exposed to everything in a 6-month set. But if you live on a lookout in northwest Montana, you're fine. You never get sick. It works out just fine. So the reachability is just a simple binary. Is it possible for one person to reach another? Distance is how much work do I have to do to get there? And this is a necessary feature because transmission is not certain. If you think about that little example I just showed you in the simulation, the same exact set of parameters generated nobody sick and everybody sick. And so the probability there is highly variable. And if you have a probability and you have a graph, what you really have is a sequence of AND conditions on top of a probability set. So I'm going to say I need to flip a heads and a heads and a heads and a heads. And so in order to get 6 steps out, I have whatever this probability is taken to that distance power across a single line of a step. And that's a very important point. So across one set, you're going to have a decreasing likelihood because it's and as you go forward. The second set, or the third sort of feature in this set, is local clustering. And so local clustering is really fun. From a geeky, mathematical, how do I understand how these things work? Clustering is interesting because it has 2 contradictory effects. On the one hand, clustering makes networks inefficient. If there's no clustering in my network, then you have a branching process. Whoever I reach, they reach more people, they reach more people, and they reach more people. And you get this wonderful branching process that spreads quickly. And so you get this thing called a spanning tree, or a directed acyclic binary graph in this case. And you have, each person is generating, they have 2 ties, they generate as many ties they have as how many new cases they bring. So if I have no clustering, I get a very efficient spread to no people because there's no wasted time reaching the same people twice. In this case, right, from an efficiency standpoint, these nodes here, they are getting reached by multiple people in the same time. So from an efficiency standpoint, that's wasted energy, right? So if the bug were perfectly transmittable, you would hate to have this because that's a waste of your time. And so from that standpoint, clustering slows infection because you end up with these longer paths. You waste a lot of time sort of reaching the same people over and again. At the same time, because of this distance effect, that same probability effect means that most of these paths are not certain. And so if your probability of infection is low, that means that the probability that I go just through this path is going to be uncertain. So this is insurance. So having clustering means that I could go this side or that side. And so it provides an or condition instead of an and condition on the reachability across the network. And that makes it possible to have more robust spread. So it moves slower, but it's more likely to move further. Right? And so it's those contrasting features, that it's lowering the efficiency of the network, but increasing the robustness, that makes clustering really interesting. We can learn some interesting things about optimal clustering, about searchability, and all kinds of fun things. As a little bit of an aside, for those of you, just to, because I'm in front, so I can do an aside. There's a wonderful series of investigations that John Skaforitz and Tom Ferraro started in the late 70s, building on work from Anatol Rappaport and a few others before him, on what are called traces through random graphs. So what's the likelihood that how many people can you reach at each remove? So from 1 step, 2 step, and 3 steps. And if I have a perfectly random graph, there's some beautiful math underneath this that lets you just write down the equation for these curves. And so I can say that I know that if my network has a certain degree and I have a certain probability, then I know exactly what this curve should look like. So the number of steps that I can reach at each step, sort of the profile of a breadth first search through the network is knowable in expectation. And that's wonderful, based just on the degree of the network. What John Skaforitz and Tom Ferraro discovered or thought about was this clustering idea of reconnecting to the same people. Takes the original equations that were something very much this recursive equation of how many people you meet at each next reserve, and added to it a series of things about this governing feature. So the only thing that's driving this curve is this one parameter. So it really is literally a 2-parameter model in this case. So what did they do? They said, well, it turns out that there are structuring events in real networks. We don't have a random number of people that we're tied to. We have some people that are random and some people that are not random. So for example, reciprocity is a structuring event. That the likelihood that I reach out to you is higher if you've reached out to me. And so that's a structuring event. Transitivity is a structuring event. Clustering by categories is a structuring event. And these things all have the effect of lowering this little alpha term by some knowable degree. So we can actually specify a difference by reciprocity and transitivity and other sort of clustering features to generalize what this parameter does and how much it drops from what we think of as a purely degree set to what's the effective degree conditional on these features. And so you can actually do a really nice job with this very simple model of fitting these curves to an observed network. This is a 7th grade school in Ad Health. And that difference between what you'd expect by random and what you see in reality is social structure. That's the things that are happening in networks that make them non-random. And it's a really fun exercise. Now, it doesn't work exactly because it turns out that there's a functional form, there's a shape of this curve implied by this set of equations that doesn't always get fit, so you'll get a funny little crosses here, so you need to switch that up a little bit. So there's some things under the hood you can do. But it's a really fun sort of modeling world that has that other people in the field, at least in the social network side of the field, haven't picked up much. So there's a whole lot of work to be done. There's a good work left to be done and build on what they've done. This is also the exact same idea behind 6 degrees of separation and other kinds of small world networks. What Duncan Watts and Skaforitz rediscovered was this notion that clustering makes it really hard for things to move through networks, but a random tie across it essentially creates that bridge, which makes it possible for us to have both efficiency and robustness simultaneously. All right, so that's my little aside on local clustering. Clustering is cool, play with it, have fun with it. The fourth thing that drives the spread of a network sort of builds on a global version of that local clustering, which is multiple routes. That robust diffusion requires that you have not just a single path that you move through, but that you have multiple paths. And the more paths I have, I get addition instead of multiplication, and so I get or conditions instead of and conditions on these probabilistic transfers across the network, and you get a higher likelihood of moving overside. Again, not certain, but much higher. And what does this look like? This is the structural cohesion idea, or node connectivity, that the more paths you have that are unblockable by someone else, the greater the likelihood that this disease is going to have a way, that a probabilistic flow through a network will have a chance to move through without hitting a bottleneck. So this was my intuition for why, if I were to vaccinate that little cluster of people in the middle, if I could find if they were effectively a group that's like a bottleneck, then if I vaccinate them, then I can contain the infection in one spot. In order for that to work, you need to have a perfect vaccine. But that's where we're at. Finally, there's this notion of sort of heterogeneity in degree, super spreaders, hubs. There's a lot of different languages for this. But the basic idea is that there are some sets of nodes that really are functional bridges. These are folks that once you reach them, they're routers that go everywhere. These are the gossips. I grew up in a very tiny, small town. My mom knew what I did before I did it. Because there were a couple women in my town who were very good at watching the neighborhood and telling my mom what I did, right? And so if you've lived in a small town, you know who those people are. They look like this. When they're quiet, you can get away with something, right? And so you can only get away with something, right, when they go away. But when they're there, they're watching the world, right? And so there are lots of ways to think about this, and it's not just degree. You can have high degree off in a corner somewhere, but you have degree that is linking to others, high betweenness and high degree. That's sort of the magic sauce to get this super spreader set. Like clustering, super spreading is complicated. There are some interesting sort of things that happen with this. If your flow is very simple, very much like that little simulation I had before, then that simulation under the hood, the model assumption is each person has opportunities to spread their bug to every person every day. But if you have a lot of ties, you can't talk with every person every day. There are natural limits to our interaction sets. And so depending on what's flowing through your network, the ability to be a super spreader, super spreaders can be super spreaders when the disease flow is easy, but they can also be bottlenecks if what's flowing through the network is something that requires amount of time and energy and efficiency for a person to work on. So there's always this interaction between the qualities of the things moving through the network and the structure of the things they move on the network, and that's what makes it interesting. And so our job is to think about, how hard is it for me to spread the notion that I should use R instead of SAS, as opposed to how hard is it for a bug to move between me versus someone else. And these are different kinds of things and different kinds of notions and different kinds of abilities to do it, but the same logic falls under SAT. Super spreading as a social phenomenon, or this sort of hub-spoke structure as a social phenomenon, is really a feature we also refer to as assortative mixing, and it's assortative mixing by degree. And so assortative mixing by degree says that if it is assortative, people with high degree mix with other people with high degree. If it's disassortative, people with high degree mix with people who have low degree. Classic disassortative network is commercial sex work. So Johns have many fewer partners than their partner who they're doing sex work with have partners. And so commercial sex networks tend to be highly disassortative, whereas everyday sort of general population sex tends to be highly assortative. And so there's a difference in the functional role of what people are onto on how they work this work. All right, questions, comments, thoughts, concerns on the structural features of how this thing works? Please. Oh yeah, that's great. Yeah, so bipartite does two things. And so and again, I'll use this graph so I can see it. If we were to imagine thinking of these as two, actually it works out well in this little example, this could be a bipartite graph of sort of clubs and people who go to those clubs. The difference is that that if you're spreading something that's going on in the network, then you're really caring about movement from here to here by virtue of the fact that we shared a space. So it's usually not the case in a bipartite network that we know the exact path structure. We treat this as a homogeneous cluster. And so they're clusters that are linked through their shared setting. And so in something like hotspots for HIV or something, sort of like dance clubs or other kinds of clubs that might be a place where people meet for commercial sex work, we haven't observed the commercial sex, we've observed the venue. And by knowing the venue, we then say that there's some probability that the people in that venue have done it. And so what we usually do with the bipartite network is, because the setting itself can't actually transmit it, and usually it's too little to say that I go from here to here and then treat this as if and go there. I usually project this to the person-to-person projection and then weight it by the size of the venue. So, or the inverse of the size of the venue. So the likelihood that you and I interact in a room of 50 is much lower than if we interact in a room of 5. And so I can do the person-to-person projection, shoot, and then reweight the ties by the inverse of the size of the set, and that is a good, first-order approximation of what the likelihood of us actually interacting with.
So it's still reduced down to actors?
Yes.
Person to person?
Right.
Interesting.
Now there are some settings, go ahead, please, yeah.
So just following up on that, what if the transmission is somewhat mediated by the environment? Like I'm thinking about COVID.
Yeah, that's exactly what I was just going to say. So there are some settings where, and this is why the flow moves through, right? So if you're in a setting where you're locked in a room with really poor circulation or an airplane, then you can actually treat that as essentially a difference of how you would weight that inverse weight by the characteristic of the setting. And there's a different kind of two-mode network where the mode itself is actually active. And so if you had, for example, the spread of information on a network, then you have readers and newspapers. And newspapers or other sort of websites, those are two different modes. Like readers don't interact with each other directly, but they interact with the same information that's being produced by the media company or whatever. And so in that case, you can treat these two modes as two different kinds of actors that are doing something very interesting, and you can model it directly as that. So there are times when a two-mode network where you do want to respect the modes as themselves, when the contagion is, in fact, mediated by a change in quality or a change in production structure by what's happening between the modes.
Well, I'm thinking like in the case of saying like with the COVID testing and the Department of Health, they're giving out free COVID tests and you're giving out information and you're looking at diffusion of information about free COVID tests so everybody doesn't know about it. You're telling your neighbors and friends, you're telling people in your community, and like that actual venue is active,
Yeah. So in that case, your node has, I wouldn't treat that as a bipartite network. I would treat that as essentially a node with two classes of qualities. So you have active nodes who are like they've come to the setting having been adopters, so they already know it, and they're broadcasters. And so they're sitting out, so they're not receiving information and flowing through, but everyone they come in contact with is effectively a new seed, usually with a low probability of adoption, right? So we don't listen to the public health department as much as we should, and so that's why it takes a lot of messaging to get through. But and it's not a diffusion process in the sense of, the public health department's not going to catch a new information thing very often from the input. So they're always going to be an output. They're going to be a source and never a sink. And so you want to keep that in mind in how you model. Please.
Yeah, I was wondering also about threshold for adoption, because I was thinking about
That's fine. So there are, I was going to try, I think, is it coming up right now? No, I was going to do that a bit. But there are some slides in here about two different kinds of threshold models for adoption. So the threshold model of adoption are what's kind of interesting about it's one of the sort of first steps of a social diffusion that gets us to peer influence. And so the beauty of the threshold models for adoption is to say that actors have agency over what they decide to do. And by virtue of that, we have differences in how we think about sort of the value of the information provided by our peers. There's two versions of that. There's the simple adoption method. I need to hear the message multiple times, and only if I hear it from a lot of, either repeatedly or lots of times, do I adopt. And there's a complex diffusion, which says not only do I need to hear it multiple times, but I need to hear it from multiple sources. And so I think the contagion model is essentially a subset of threshold models. I think some people will disagree with that, but The basic idea is that there's a variance in both the amount of information I learn and the sources of that information that I can learn. And each of us are more or less susceptible. Some of my crazy uncles, they believe anything anybody tells them, right? And so they have a very low threshold for adopting conspiracy theories. Hopefully, the people in this room, we, by virtue of our training, have come to a much more critical sort of understanding of the adoption of conspiracy models. Right? And so that's be a good example, I think, of those two different sets. Does that help? Please. Yeah, this is great. These questions are probably much better than what I planned to say. So that's.
Adopt the threshold, adjust it, because like my threshold can change. Say,
Yes.
Think about other models like trans-theoretical model. I know diffusion animations, you have that, but like what about other social behavioral models that talk about my readiness to adopt, and that can change depending on other social contextual factors that happen.
Yeah, exactly. So there's you've just, I think what I heard from you are at least two, maybe three different models for how threshold change. And absolutely true. So thresholds are not static. And so people's thresholds change based on the context. So what are the different kinds of things we're learning about? So I might have one threshold for news and different thresholds for sources and so forth. There's also, I think, a developmental sort of change. So I become set in my ways, right? Or I'm not. And there's also a contagion effect of thresholds. So it might be the fact that I not only believe certain things, but there's a second order my propensity to believe new things might shift over time as a function of hanging out with people who also believe new things more readily. So how do you fall down a conspiracy theory rabbit hole? You hang out with lots of other conspiracy theorists who also believe these things, and they sort of make you sensitive to the things they believe, and that lowers your threshold for these kinds of information. Is that a fair summary, Tom? Okay. I feel a little bad. I mean, the guy who literally wrote the book on threshold models of diffusion is sitting in the back of the room. So, please.
Yeah, the word that connected with measles, thank you, Estelle. Yeah, I was trying to think about the measles epidemic.
Mm-hmm.
You would think that the threshold for adoption of vaccination would be a child that your family dies, or somebody close to you dies. But we are hearing on the news these very these grieving families that even though they are grieving so deeply, they are not adopting vaccinations, or their kids are not being vaccinated, their remaining kids are not being vaccinated because they are
Mennonites, right.
Mennonites, there's a religious.
Mm-hmm.
So how do we also account for these contextual features in our
Yeah.
when we think about
So the question is, so it's puzzling why people who experience loss for not having done something like adopted the measles don't then turn around and adopt the measles. And how do we account, and as a specific case for a general set of classes, is how do we account for the ways in which contexts affect the ways, like religion or something like that?
because when you think about also the world, when people into Vietnam, people start turning against the Vietnam War as they start losing people close to them, right? They start sending people to Vietnam, they're close to them, and they start coming back with some sort of having lost
Right.
leg or something, or they start literally losing people, so people start saying, hey, there's something wrong
Right.
about that.
And I think what's great about these two examples, I think, are really quite nice, because the measles example, should I get my kid vaccinated, and why wouldn't I be more likely to get them vaccinated after my child, other children vaccinated after my child has died? And the other example, if you couldn't hear in the back of the room, is people coming back from the Vietnam War, recognizing that they've lost loved ones, and they start becoming more anti-war as people are coming back. The beauty of those two differences is agency. So the problem with my vaccinating my second son, if my first son dies, is I have to admit that I killed my first son. And no one's going to do that, right? So you can't get yourself out of a hole without blackening yourself, is Zygmunt Bauman's word for this. And this is the reason that that evil is ratcheted. It's really hard when people start committing things to undo it, because you have to recognize your problem. Going to war and losing a brother in the war, that's not my fault. I didn't send him to war, right? The government sent him to war. And so it's a change of agency. Now, that would be my hypothesis. The beauty of these kinds of things is that there are different, this is this beauty, I mean, this is the twisted world we live in, but it's an interesting question, and I think it would be really fun to sort of to turn out, whether is it not fun, it'd be really scientifically informative to understand whether or not people who have lost loved ones, their likelihood of picking up the action to prevent that loss is inversely related to their sense of agency on the initial sort of set. That would be a good hypothesis, but I don't know that it's true. Please.
I imagine it'd be a good context for a multi-method study where you're doing quantitative and observing that, and you sample those things that kind of don't make sense. Those
Right.
nodes, and you remove the quality of that to answer how you talk.
Yeah.
I imagine.
I mean, and this is one of the things that makes social diffusion so much more difficult than disease diffusion, which is already really difficult, right? Is because you have all of the sort of features that have to do with the network side and the probability side and the testing side and the measurement side and all of that. And then you have human social creativity, which allows us for adoption to twist the meaning of the thing that gives us impetus for adoption. So my susceptibility depends on an idea, it depends on how I interpret that idea and what frame I put it in and what these actions are done. And so there's always I'm going to get into social theory, but there's always a second order problem of how I know things and the ways in which how I know one thing affects the other things I believe that occurs within a social diffusion that isn't necessarily the case with an immunity. That if I happen to be, if I have the vaccine, I'm much more likely to be immune to the bug whether I think about it or not. It doesn't depend on what I think about. And so there's not that sort of second order feedback process that happens in social diffusion. And this is why the adoption of innovations has been such a rich theory for us to play with over all the years, because these innovations are there. All right. It's 12:30. So is lunch on its way? All right, so I'm going to keep yammering for another at least maybe 5 or 10 minutes. I just want a couple more things I want to say just about this. There's a whole series of things in these slides about the dynamic networks and how timing affects the spread. The take-home message here that I'm just going to get to at the very end is that there's lots of sequence features of networks that matter for the spread of something over a dynamic network. But the key one binary thing, if you needed to know it, is this concept known as concurrency, which is that things move through networks faster when edges are held at the same time versus when they're unfolding in sequence. And the reason for that is there's an actual path structure reason for it, which is easier to show right here, which is that if relationships happen in sequence, all your indirect ties have to be asymmetric. If the relationships happen in parallel, if they overlap in time, your indirect ties become symmetric. And so every overlap and concurrent relationship creates a two-way path as opposed to a one-way path. And that is as necessary for the spread of disease as birth rates are to the growth of a population. I mean, it is literally a mechanistic feature for the potential exposure graph that's underlying the spread of diseases. So it has to be effective, and the question is why is it effective in some places and not effective in others? And the reason has to do with that multiple paths. If they're already there, there's no room for concurrency to matter. So if I'm living in worlds that have very cohesive, lots of multiple paths in the network already, then the fact that my networks overlap in time has no effect. And so you're going to find, in a classic regression sort of sense, zero effective concurrency. But if I have really sparse networks, I'm going to have a really strong effect, because that insurance that comes from those multiplied ties matters a lot more. Again, read the slides or come talk to me. This is actually, from a geeky standpoint, really, really interesting. But in the interest of time, I'm going to go away from it. The second thing I want to talk about is, where did it go? I wanted to spend a little bit of time, just 2 minutes, talking about peer influence. So the thing that makes peer influence a little bit different than the adoption of behaviors is that peer influence, when we typically think about it, we think about it as a continuous outcome as opposed to a binary outcome. So I don't just take something, we negotiate something. So we influence each other. And the classic model of this is coming out of Noah Friedkin's work, which is the structural theory of social influence. And this model is, this theory is built around these two equations, which we're going to combine in a second. And the theory says that everybody at time one, sort of in a tabula rasa sort of sense, their beliefs and practices are determined by their characteristics. So I have some series of attributes. I'm a balding white old man, and a series of parameters that govern the likelihood that I believe something because of those contours. And those are your classic, that's a classic sociology sort of rectangular regression. That's all that is. Then we add to that, at each time step, we adjust our beliefs and practices as a function of our peers' beliefs and practices, that's what this is, and our initial belief and practice, right? And so those things are balanced. So the beauty of this kind of a model says that whatever we believe to start with is always there to some weighted degree with what our peers are doing. And so it's a really clever little model. And what's nice about it is that we can sort of rearrange terms a little bit and write this in a nice way. And it turns out that at equilibrium, if you let this go on a long, long time, that the model will take this convergent form. You'll end up with a balanced effect. My outcome is a balancing of my peers and my initial set. Now, if the peer influence effect is really small, if this is 0, this goes to 1, and essentially, this goes away, and there is no peer influence, right? And so that my attributes are determinative. That's the classic sort of non-network structural sociology story, that everything about my world and the growing up is already captured here. The peers are epiphenomenal. If the peer influence model is working, what it's saying is that this would go to 1 in limit, this would go to 0, and my values are determined entirely by the peers around me. This is the smell example or the book club example that Craig gave us yesterday. The thing that people don't realize about this model and some of the beautiful extensions of it are that the peer influence need not be a single parameter. It can be a vector. Each of us can have a different susceptibility, just like we have different thresholds to adoption. And we also have multiple different ways that we can specify this weight matrix. This weight matrix, I went over this way too fast, but this weight matrix is a row normalized adjacency matrix. It's how much each of my peers has an influence on me. And so it's a nice way to think about our peers, but we can weight this a lot differently. So there's a lot of work in peer influence models that have adjusted who's influential to us and how likely we are to be receptive to influence. And I like thinking of these as simulations. Some of you have seen some of these before, but here's a very simple 2-parameter. So there's only 2 values in that alpha sort of vector. So either you are a peer leader in which you have 0 group peer influence, or you're somebody else in which your peer influence is moderate. I don't remember what I've set it at in this simulation. And in this, what you're seeing in front of you here is a belief space. So you have people who hold beliefs about one feature and a second feature. Could be the value of the environment, the value of global trade, right? Just whatever. It doesn't matter in our case. I just use 2 dimensions because it looks pretty. We can wash it. And so what happens in a world like this? Well, it turns out that group leaders, because they have no peer influence, they don't really move. I must have had it not quite at 0. It must have been just very small. But peer leaders, this theory predicts that peer leaders create polarization. They create people to be moved off by virtue of being anchors. And so what the anchoring effect does is it sort of strings along everyone else, even if they are perfectly reasonable. And even if it's not your crazy uncle from Montana, it's instead perfectly reasonable, rational actors who are discussing in a consensus way that this model predicts. If the social system has anchors, then that's going to, and we are differentially exposed to anchors, the model's going to predict this kind of high heterogeneity in the underlying belief space. And what I like about this model is that it really is incredibly flexible. So you can go back to this, and you can expand multiple different types of relations. So I might have peer influence through kin. I'll have another peer influence through friends, another through coworkers, another through media. You can specify this as richly as you think your theory desires. And you can have lots of different weighting internals. So there's lots of work you can do here to do really interesting things. Now, there's a problem with all of this work, and I'm just going to, that's estimation features. I'm going to jump over this. The problem with all of this work is that networks are complicated, right? So 2 things are usually changing simultaneously. Our relations are changing, and our attitudes and behaviors and beliefs are changing. And so at any given point in time, I can't know that the association between my peers and my behavior is a function of having been influenced by them because we're reasonable people and talk to each other, or because I'm a stubborn old puss and I only hang out with people who already agree with me, right? So is it selection or is it influence? And the selection or influence process is fundamentally unidentified, right? They're just like every model is fundamentally unidentified if you're willing to go back far enough in your specification space, right? And so the fear is twofold. One is that there is a reverse causality, that your outcome determines who you like. And the second is a selection, that because I like you, I make you as a peer instead. And these are subtly different features. The second one should be instead that there are other features that drove us to be peers other than the thing we've measured, right? And so we don't know those things. And this debate was sort of put under a spotlight when Christakis and Fowler published their work in the New England Journal of Medicine. That just kicked off a firestorm of this, and we've now spent 15 years thinking about the problems with those papers. And I think, as Craig pointed out, the problems with those papers were real, but the solution may have well nonetheless been right. Right? So they might have had the wrong model for the right outcome, but we learned a lot one way or the other. And one of the things that we learned as modelers, and I love this, debate sort of played out on a web group that many of us are on called SOCNet, which Tom Schneider's argued that the logical consequence of this sort of way of thinking about network causality is that we're stuck with imperfect methods. Others argue that though only perfect methods are acceptable, and while applauding such lofty ideals, I still believe that we should accept imperfection. In life, as in science, progress is made by discussion and improvement of imperfections, not by their eradications. So if you're out there looking for a perfect model, and you only accept an experimental result in order to prove causality, which is about the best we can do, you're not going to find it. And as a community of science, we shouldn't find it. That shouldn't be we shouldn't hold ourselves to that gold standard. And for any of you who have, this is a pretty multidimensional group, if you've ever been around your favorite cranky economist who can always find, whose game is to find the ghost in the machine that might be making your results heterogeneous or endogenous, right? This is models saying, yep, that's surely there. How do we get around it? In practice, there's been a couple of different models to get around it. My favorite models are to deal with what we're going to call stochastic actor models, and this is what we're going to talk about here in a bit. The other sort of standard model is this thing called instrumental variable modeling. And instrumental variable modeling says, I'm interested in sort of this correlation, the unique effect of x2 on y. And so what I need to do is find some instrument that is correlated with x2 and not necessarily with anything else that would be in there. And then I can estimate the overlap here and use this as an instrument for that. Notice what happens when I just made that little switch. The conditions that require an instrument necessarily make the information that you have to determine the unique effect smaller. Instruments have to be imperfect. They can't be perfect, or you would just have the same thing that you do otherwise. Very rarely, there's some really clever things that come up that are you get a lot bigger red region than this, but in general, any instrumental effect is always going to be a trade-off between certainty of that one coefficient and power of your sample. And so you're going to effectively have a much smaller sample size because the power implied by the instrument makes your world a lot smaller. So you end up with very conservative results. And I think the nice thing about the nice thing about this is it's rigorous, it's interesting. You can often have some really fun discussions about what makes a good. It's a good drinking game to figure out what makes a good instrument. But we've done that now for many years, and the answer we've come up with for most of this effect has been that. Is it selection or is it influence? It's both. I have almost never seen a really well-running model that doesn't say, yep, it's both. Just like, is it nature or is it nurture? Yep, it's both. So the question is not, does peer influence exist? The question for theorists and for people who are trying to do work in this field is to think about how the peer influence works. And our assumption at this point, after 20 years of doing this work, should be that yes, our measures of peer influence are going to be contaminated by other kinds of upstream features that we can't necessarily control for. But take knock 20% off them, and you're probably close to the ballpark of where you should be. As it turns out, there's a good way to do that, which are sensitivity analyses. And Ken Frank teaches a week-long course on generating models for sensitivity analysis. There are both model specification sensitivity analyses and effect size sensitivity analyses, which allow you to respond to your grumpy economist in the seminar by saying, yes, it's possible that the ghost under the bed will make this go away, but that ghost would have to be really, really, really big and really, really, really scary. And there's nothing in the world that possibly conforts to that to make this effect go away. And so those kinds of sensitivity models turn what's a binary question, endogenous or not, into a continuous question. How endogenous does it have to be before my inference is threatened? And that's a much easier world to play with, because everything is endogenous on a binary set, but most things aren't so terribly endogenous that they're going to undo our models and undo our general understanding of the world. And now I'll get off my soapbox and let you have lunch. Questions or comments before, or you can catch me at the end. All right, let's go, guys. Get some lunch.